welcome. First of all, uh, yeah, I realized after streaming last time that there's two main reasons I'd like to here. I'd like to stream. The first one is teaching hardcore maths and helping you understanding you out there understanding mathematical terms, being able to do multiplication, fractions, power rules, anything really, integration, vectors, whatever. I'll introduce you to things if you'd like to hear about them. I'll answer your questions about things. Could be volume calculations, surface calculations. The other reason is because there's something more about maths that I find fascinating. I find it fascinating that you're able to calculate all these things. We've created all these brilliant ideas or constellations of the numbers, and I mean, coming up with the natural numbers 1, 2, 3, and so on. That's I mean, very very good. They're very useful, as I talked about in my first episode. But it's not all that brilliant. They do some very very nice things, but there's like the negative numbers. They are a little bit more constructed. It's not something that we are around in our everyday lives. It's a construct, really. Yeah, fractions is a construct. The real numbers, the for instance pi is a very nice real non-rational number. They are very constructed. They have infinite. They go on forever. You may have heard this. They have infinitely many digits. Yeah. Functions and sets and all that sort of thing are all constructs, and they are very nice, and they can do very many things, and they describe the world really nicely. Like quantum physics, there would be absolutely no quantum physics without mathematics. There would be no computers without mathematics, no algorithms. There would be no cryptography without mathematics. At least not in the sense that we have nowadays, and then in the sense that we need with the computers we have nowadays. And all that is fantastic, awesome, brilliant. But I think there's another strength to mathematics, which is understanding the world. The way of thinking is not as much directly applicable to the world, but it's just sort of how our brains work. Last time I was talking about sets. One of the reasons I find set theory interesting is because it works in sort of the same way that our brain works, I think. Or I should maybe say our language. Because I think our language is, well, a set of sets. It's in our language there's different sets. For instance, there's the set of all green things. Really nice set, very easily definable. Yeah. And then there's subset. So this is all green things. This is an automatic set in our language, I'd say, anyway. And then there's different subsets, right? Could be leaves, for instance. Green cars. Oops. Yeah. Yeah, and of course there's a million of these. Yeah. The point is, mathematics is a stricter way of looking, or a more rigid way of thinking about the things, thinking of things that we do already. So we already do this, is what I'm trying to say. Mathematics just does it more strictly, and by understanding that it's how it works out in mathematics, we can get a better of an understanding of how our minds work, how we work ourselves. And I find understanding myself very fascinating, because that helps me understanding the world around me, and it helps me understand other people. and I think that's, well, I don't want to say that's what we live for, but it's a pretty big thing here in life, and I don't think our world would work as well as it does without us understanding each other. Yeah. There's a bunch of things like this up there that that mathematics helps us by giving a slightly different view of. Our minds are not as strict as mathematics. For instance, we might consider trees green, and I don't know if I might consider trees green, but they wouldn't be just green; they'd be brown as well. It's not quite as strict as the maths behind it. The whole how mathematics relates to how we think about the world is not something I'm educated in. I don't know specifically much about it, because you can't. There's no study of this field. It's not a field even. It's just something I'd like to do. What I know is the more hardcore maths. So the whole understanding how our world works is a journey, I'd say, and it's a journey for me, and I hope it'll be a journey for you. Even though I don't think I don't have an education in it, I still have some ideas, and what I do have a part of an education in is mathematics, the pure one, and oftentimes, surprisingly often, I've seen connections between how I think about the world and how the mathematics work. Of course, the maths is more rigid, but still, there's a surprising amount of relation. Yeah, because I very much think of the world in numbers, in terms of numbers. For instance, if I see something in front of me, I will immediately categorize it based on how many of them there are. I mean, it's printed into our knowledge that we have 8 fingers and 2 thumbs. Sometimes I think I know the truth about the world, but then if I use the mathematical sense in which it works, I don't know the truth anymore. And I'd like to do an example of this. This is not completely by imagination, but someone brought it to my attention. If this is the set, and again I will go with set theory, I hope you know it. If not, you can watch my YouTube video, which will be up hopefully by tomorrow, from last time. If this was the set of all Germans, yeah, and let's pretend that we don't live right next to Germany. If you do, let's pretend we live in China or on the moon, somewhere far away from Germany. So we don't know very much about Germany, and we don't know very much about the Germans. But what we do know is we know about a guy called Hitler. Yeah. And I don't know how to spell this, but I believe this is the name of Hitler's second in command, pretty much, Goebbels. I don't bother with the historical details. I'm not a historian. I bother with the maths, because that's what I find interesting. And let's say that we know that there are criminal people, and we do consider Hitler and Goebbels to be. No, I should do this like this. Yeah. We do know that Hitler and Goebbels should be in the set of criminal people. Yeah. And if we only know these 2 Germans, all the people in the German set are also in the set of criminal people. And of course out here there'll be other criminal people from our country or from other countries, whatever. Yeah. Then let's pretend that this represents people. So let's say that we are now told about, we still live far away from Germany, but we're told about some Germans, but we're only told about criminal German people. So this continues to be the picture that all German people are criminals. And at some point, this, for I think most people, turns into, well, if that it turns into if you're German, that means you're criminal, because that's the situation right now. Right now, if you're in the set of German people, you're also in the set of criminal people. Of course, there's criminals who aren't German, but that's not important. I will do a little bit of mathematical notation. German, yeah, like means this is proper mathematical notation. And when if we have this picture, we might then get to a point where we say, if we hear about another German person, we will automatically assume that he's in this set. The tendency for human beings, I think, is to think, well, then that person must be a criminal as well. But that's not the case, is it though? And I don't exactly know how I'm going to do this. The case is instead that there's part of the Germans who are not criminal. In fact, the line would probably go somewhere here. I'll just try and fill in this, just to make it look a little bit nicer. Yeah, there we are. There's some German people in the set of criminals, but there's also some German people outside the set of criminals. And this distinction, this isn't always true. You know, that's the thing that we sometimes forget, and this is a very real thing for, at least here in Europe, when immigrants come into a country. If we hear about a lot of people from a country who are criminals, we sometimes, if we then come across another person from that country, we sometimes say we sometimes think automatically that that person's a criminal as well. Well, this is the basis of racism. Remove German and put in any other nationality, and this is racism. Because just because you're in the set of Germans doesn't mean that you're in the set of criminal people, as clearly illustrated here. The very first bit of notation I'll do over here. You may recognize a certain portion of this notation. This means the natural numbers. This would be the numbers 0, 1, 2, 3, 4, and so on. These are to denote a set, because this is actually a set. This is the set of all natural numbers. Sometimes 0 will be in there, sometimes it won't. The next set, and this is again a set of numbers, which will be reasonably easy. These are the whole numbers. The set with the funny line means the whole numbers. So this will be all minus 3, minus 2, oh, whoops, minus 1. God, this is 2, 3, comma, dot, dot, dot. Of course, you'll notice something about these two, that this is contained within this. The sign I want to use now is this sign. It means contained in, and this is how it normally looks, well, sort of. And right now I'll just turn it, doesn't matter, you can do that in maths. What's interesting about this, I find, is that math turns out to be not just something, I don't know, something, a system of logic, which it is, but it's actually also a language. And the nice thing is that it's an international language. I mean, the symbols that I have learned here in Denmark are exactly the same as the ones they learn in China or the American. So this one is a little bit harder to write, and therefore I will just do like this. Q is the set of all fractions. So they'll notice that in here b can't be 0, because you can't divide by 0, that's not defined. So that doesn't work. And so this is a is a number from the whole numbers, and b is a number from the whole numbers. And any number at all. Yeah, this is how we like to do it at university. To write letters instead of numbers, because then it could be any number. And it's much faster, as you might imagine, writing down one letter over another letter than writing out all the numbers, because that would take some time. Yeah, then someone might say that 0 is not in here, but yes it is, because a can be 0, and if b is any other number, then this is 0. So this is all the fractions. Oh, well, what I want to do is move it. Oh, well, I like to move it. Yep, up here, and we'll just do another one. Because again, these are contained in this. If you write out the proper fractions, you'll get, if you put in numbers from here, the right numbers from here in here, you'll get the numbers from up here. Maybe you'll know this as well. It's the real numbers. The r's is real. But what are the real numbers? Well, as you might have guessed, we'd like the fractions to be in there, because it'd be nice to have them all the way down. This means all numbers. Yeah. And a very nice example of a number which is here and not here is pi. Pi cannot be expressed as a fraction. Yeah. And another very good number that which is in here but not in here is the square root of 2. I will not go into details with why the square root of 2 cannot be in here, but it actually can't, and I believe on YouTube there's a very nice video by Numberphile that explains this. Well, that doesn't explain it, but proves it mathematically. And the difference from these numbers, the rational numbers, to the irrational numbers, or the real numbers, is that, of course, all these are in here, and there's some more. What's more in the rational one? Well, there's the infinite numbers that aren't repeating at some point. Yeah. Pi, for instance, it doesn't start over. What's after the decimal point doesn't come again at some point. It doesn't start over. It keeps being something new, something changing, and it does that infinitely. You could go as far out as possible, and there'd still be infinitely many numbers ahead of you. There's still something ahead of you, no matter how far out you go. The number, very nice number. Oh no, this is the one. 0.3333 recurring. This is infinite, yeah, and it's in here, but actually it's in here as well, because this can be expressed as a fraction. It'll be 1 divided by 3, so it'll be, this belongs in the fractions. And this gives me a nice opportunity to make another tiny bit of notation. I will try and draw it with my mouse. It's this. Sort of looks like an E, but it's more bendy in the shape, and it can turn anyway as well. It means this is an element of this. It's one of the bits that this set is made up of. So an easy one, for instance, would be 1 is an element in this set. 1 is also an element in this set. And this is where it gets a little bit, at least a little bit, mathy. Let's do an somewhat interesting number. 17. I'd like to make this shorter, and then move it over there. So this. Oh, that was a little bit big. That's a little bit ugly. We'll try again. Yeah. I guess you should really do this on paper, where I can actually draw them nicely. Oh well. 17 is an element of the natural numbers. Since we know that the natural numbers is contained, the natural numbers are contained within the whole numbers, and the whole numbers are contained within the rational numbers, and the rational numbers are contained within the real numbers. That means then that we can write this. I need to go with the pencil. This is the same symbol as I used before. 17 is element of the natural numbers. That, since the natural numbers are contained in the real numbers, that means that 17 is what I like to write. 17 is, and here we get to get the chance to see it the other way around. It's a little bit easier to draw. Part of the real numbers. So 17 is an element in the natural numbers. That means that 17 is an element in the real numbers, and it's because of this chain. And this is, if you think about it, this is, I mean, it's, you don't even have to actually think about it really, because it's just sort of a no-brainer. 17 is a natural number. No, 17 is part of the real numbers. Of course it has to be. But this is the more mathematical reasoning behind why is 17 actually a real number as well as a natural number. Because it's a whole number as well. It's a rational number. I think that was what I said wrongly, but it's still right, and it's a real number too. Yeah, and now is the point when it gets even more exciting. So this is the complex numbers. It turns out, even though this is pretty much any number we can imagine, and a few more that we can't imagine. Oh yeah, another nice number which is in here is the number 1.2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'll just write all the numbers. 6. Well, I won't assume 11. And it just goes on. This is a irrational number. It's real, but it's not in the rational numbers, because this keeps going on forever, and it won't repeat itself. It'll always be something new on the end. And I'll just quickly try and do this one. Yeah, it's part of the real numbers. Yeah. So, and this number is pretty hard to imagine. Yeah, imagine, but it has some fun properties though. Your phone number's in here. Just you might want to be careful. And your social security number or CPR number is in here as well. And your address, of course, that might be sooner, because I don't know, if you lived in number, let's say 36, you only have to go up to the number 36. But your phone number will be in there. You just have to go up to whatever your phone number is, that number, which might be pretty far out there, but eventually you'll get there. If we translated each number into a letter, each letter into a number, and so we interpreted this number as letters, at some point your name would be there, my name would be there, any novel would be in there, the entire Lord of the Rings, the entire works of Shakespeare will be in there somewhere. We just have to go far enough to see the right combination of numbers, but it'll be there eventually, because all combinations of numbers are in here. I find that amazing. This number is itself, I don't think that has a number, has a name. No, unfortunately not. It's just a funny one. But the same goes for pi though. Yeah. With a probability of 1, the same goes for pi. So most likely it goes for pi as well. Yeah. So the complex numbers, what are those then? Well, it turns out, I don't want to talk about what those are, but there's something we can't do with the real numbers. Even with all these great numbers, with all the strange properties that they have, there's some things we can't do. Just imagine. Yeah. And you may have guessed it, it's square roots. No, it's not just square roots, it's square roots of negative numbers. I will do it over here. That may have been the wrong one. No, it's alright. Yeah, square root of -1. Yeah. Which value is this? We know what the we know what the square root of 1 is supposed to be, because TI can tell me this is 1. What this means, of course, is which number multiplied by itself should be 1. But there's no number that multiplied with itself gives minus 1. Because if we did, well, a good candidate might be 1. So let's do 1 times 1. We'll do this, and oh, that's 1. No, never mind. Minus 1 times 1. No, that doesn't work out, because it has to be the same number, doesn't it? So it has to be minus 1 times 1, minus 1. But of course that gives 1. Minus gives plus. So we'd have to do minus 1 times 1, but that's not a square root. That's not one number. That's two different numbers. Yeah. Evaluation error, non-real result. We can't do this in the real numbers. Well, I guess we'll have to not. Damn it. You can't see, but I'm crossing my arms. I'll just do this and maybe almost. Mathematicians like to give meaning to things, and they like to give meaning to this as well. This is square root of a negative minus 1. So what they do is they give this a name. It doesn't have a name already. Give it a new name. It's a pretty good rule in maths. At least for professional mathematicians. Doesn't work out too well in your exams, unfortunately. Yeah. And what will we do with this? We'll call it I. Why? No reason. Let's just do it. Oh, it has to be... Oh, I know. Yeah, I. And this program makes it italic, so that you know it's this I, not just any I. Square root of minus 1 equals I. Let's try this. What does this do for us? Well, it makes sure that there is something that'll give us minus 1 if we square it. It doesn't completely make sense right now what this should be, but it's there. Now I have constructed it. Some 100 years, some mathematicians constructed it, and now it's there. And this, they have made the rule that this makes sense, and it's consistent with other maths, luckily, and that's why it's still a rule and not just something we've left out. The thing is now that this allows us to do something interesting. Because now we can take the square root of negative 1. If anyone asks us what's the square root of negative 1, well, that's I. And then they say, what the fuck are you talking about? And you say, well, I've decided that it's called I. So now it is. What I'll do is write as 2 square roots. I say that this is the same. I can show you that my program thinks it's the same as well, but that's okay. It's calculation rules. And then, well, what is this? This we can actually figure out, can't we? Here we are. Yeah, because we know, and I will just put in an equal sign. Yeah. Because we know what this is, the square root of 17. Approximate. We know what this is. We exactly know what this is supposed to be. This is supposed to be I. It doesn't say a thing, but you know, it's just something that we'd like to say, and it turns out to work really well. And this number we know, the 17 part, the square root of 17. Apparently that's 4.12311. Something more. Don't worry, there'll be more back there. We can take the square root of negative numbers now as well, because we just split it into the negative part and the positive and the rest. So like we'd take this the -1 out in a square root of its own, and then we calculate this. Yeah, and that worked well because we can now do square roots of anything we'd like to. Yeah. And the trick now with the complex numbers is that we use this. We call this a number. This 4 point something 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 times I. We call that a number now, and I is a number as well. We called it a number. It's sort of strange because we were used to that it was only these numbers. It were only these numbers that were considered numbers. But now we'd like to consider this numbers as well. And if we consider this numbers, we can consider this a number, and we can get to that point where we can take the square root of anything. A times bi. And well, you know what I is. What I'd like to tell you now is that A and B are real numbers, as you might have expected. So this is a complex number which will have the form of 0 plus 4.12311 times I. A will be 0, B will be 4.123. Yeah, and I is still the square root of -1. This 5 is a real number. It's also a natural number. Up there somewhere are the natural numbers. It's a whole number and rational number and all that jazz. But then I'll add an imaginary part. Let's say 3 times I. And now it is not a whole number. It's not a natural number. It's not a rational number. It's not an irrational number or a real number. It's a complex number. Yeah. Course, the two real parts of this, they are each natural numbers, but the number as a whole, you can only think of it as a complex number. Yeah, and what's fun then is that, and this is the way to write a complex number. This is the general way of writing a complex number. Yeah, and what you can then do is add another complex number. Let's say 8 plus 4.2 times I. So this makes a new imaginary or complex number. So this is one complex number, and this is another complex number with a real part and an imaginary part, and the other complex number as well has a real part and an imaginary part. It's what you call these, as you may imagine. It does make sense, I believe. The A is the real part, B is the imaginary part, and you can add them together and you get a new imaginary or a new complex number. And how is this made? Well, it's quite simple, really. It's just, as you might have guessed, the first of the two added together, the two real parts added together, and the back two added together. You can see that 3 plus 4.2 is 7.2, clearly. And then it's multiplied by I, but that's just normal calculation rules. And let's do multiplication. Let's change this around. And make it multiplication. So we can multiply two complex numbers together, and we'll get a new complex number. How is this done? Well, it's more difficult than just multiplying this and this, and that and that. As you can tell, because 5 times 8 is 40, and this is different from 40, very different. Yeah, what we instead do, I'll just go through it step by step, because what I have to do instead is use multiplication, use the proper multiplication rules. So this will be 5 times 8 plus these two added multiplied together, and this one multiplied with that one. 5 multiplied with 4.2 times I. As long as I'm writing, it's a little bit cluttered. It's a little bit strange to look at, but when I write it out, it'll make when I finish it, it will look as nice as this one. 3 times I. So this multiplied with each of these, and then this multiplied with each of these. This should be proper I. This should be multiplied with 8, and then I need to add the last bit, which will be 3 times I plus multiplied with 4.2 times I. Oops. This is how you multiply two parentheses together, two brackets together. The first one multiplied with these two second ones, added to the second one, multiplied with the two last ones, and of course all gets plus. So this bit, so I'll just write the next line. 5 times 8, that's 40, plus 5 times 4.2. Ugh, I'm regretting that already. Well, that's 21, I think. Times I, has to be the proper I, plus 3 times 8, that's 24, times I, plus, and then comes this last bit, 3 times, this is 12, the 3 times 4.2, that's 12.6, I believe, and then it's times I squared. But we know what this is, don't we? We know that I squared is minus 1. Yeah, so this becomes minus 12.6, and maybe you'll now see clearly what it makes altogether. Yeah, because this will be, because I can put together the 40, and this will then be minus, because this I squared, it looks very complicated, doesn't it? I squared, but really it just means minus 1. So it's multiplied with minus 1. It just gets a minus ahead of it instead of a plus. Yeah, it's fun in math. Sometimes you can express something very simple by something very complicated. If you know the normal distribution, the integral of the complete normal distribution is probably the hardest way to write one. You can go look that up if you like. 40 minus 12.6, that will make 27.4. That makes sense to me. And then we'll add these two together. That'll make 45 times I. Well, lo and behold, we have seen this before. We have seen it right up here. That's what it was supposed to become. That's what the program says anyway. And this is the way to do multiplication with imaginary numbers. To sum it up, there's the natural numbers are a subgroup, a part of or a subgroup of, is the proper term, of the whole numbers. The whole numbers are a subgroup of the rational numbers. The rational numbers are a subgroup of the real numbers, and the real numbers are a subgroup of the complex numbers. Then there's this funny sign, which means is an element of. 17 is an element of the natural numbers. A third is an element of the rational numbers, and if 17 is an element of the natural numbers, which is what this very long and spaced out line means, then 17 is part of the real numbers, because the real numbers contain the natural numbers. This is how we prove things in maths. It's the same sort of logic that goes behind it. You can't go the other way. Or what I mean is you can't necessarily go the other way. If we know that 17 is part of the real numbers, that doesn't mean that 17 is part of the natural numbers. It is, but it's not always the case. If we have something, let's say an A, so let's say that A is one of the real numbers. Does that mean that A is one of the natural numbers? Is this true? No, it's not. And why is this not true? Well, we can take this number, just take this number, and realize that this is not natural, because this has decimal points, and that means that it's not a natural number. It's just simply not. Any number with decimals is not a natural number. And I would like to draw this with circles and think of it in terms of sets. I will this time remember the complex numbers. There's the complex numbers. There's the real numbers. Then there's the fractions. The whole numbers. Oh, these aren't completely nicely drawn, but whatever. And inside of that, there's the natural numbers. The natural numbers are in the middle, because I hope you can still see this. It's still the n. It's just the n. Natural numbers are in the middle, because they're contained within the whole numbers. And they are again contained, of course. In the rational numbers. And I hope you catch where I'm going with this. My writing is a bit... I should say that my writing is a bit wonky, because I'm using paint and it's not exactly optimal. It's just the normal letters with the lines through them. That's all it is. These, and they are pretty much correctly set, but it's just a straight line or a sloped line through them. This set goes that way. Yeah. Yeah. So all the natural numbers are in here, and they are inside the whole numbers, who are again inside the rational numbers and the real numbers, and all the way out to the complex numbers. Yeah. This gives, I think, a nice way of thinking about it, because this tells you that there are numbers in the natural numbers, and they are also in the complex numbers. If they're in the tiny circle is inside the big circle, so what's in the tiny circles is also in the big circle. Yeah, that should make somewhat sense, hopefully. If we know that something is somewhere in the big circle, it could be here, it could be here, it could be here, it could be there, it could be there, anywhere in the big circle. We don't know that it's in the tiny circle. We don't know that, because it could be out here. If we take a random real number, that doesn't show. A random real number, it could be not in this. For instance, this one, if I were to draw it, I'd draw it. Let's get it. You can barely see that. This one I'd draw out there. The I itself I'd draw out there, along with this number and this number and any other number I could think of. Yeah. And now you know a little bit of the mathematical language. A fair amount, I'd say. Yeah. Bye.